safe and sound. On behalf of ISI Bangalore students, I welcome all of you to this lecture. I have great pleasure in welcoming Professor Somnath Basu to this platform. Professor Basu is currently an assistant professor of mathematics and statistics at ISER Kolkata. He obtained his PhD in mathematics from Stony Brook University, and his research interest is in algebraic topology. With great honor, I welcome the professor who will be talking about games on graphs.
All right. Thank you. Thank you, the whole Limit team, ISI Bangalore, and in particular Sanjay, and whom I had corresponded with, for inviting me to give this talk. So this is mostly going to be a talk which is fun and games, and then there'll be some mathematics along the way. All right. So I hope I'm audible to everyone, right?
Yes, sir.
Yes, sir.
All right. So let me just share the screen and then we'll get started.
Sir, would you like to take up questions in between the lecture, or you want to prefer?
Yeah, sure. So since I can only sort of focus on the screen, if anybody writes something in the chat, just feel free to stop me and then ask me questions. Absolutely, yes.
Okay, sir.
Yeah.
Thank you, sir.
So it's very interactive. So so if there is any question regarding the rules of the game or anything which is unclear, feel free to stop. Yeah. Okay, so we are going to talk about games on graphs, and as you can imagine, a graph for us is not going to be the graph of a function, but it's going to be the graph in the sense of graph theory, or in the sense of how the subfield of graph theory deals with certain kind of objects called graphs in mathematics. So that those are the kind of graphs we'll talk about. So we'll get to know what they are formally. Games, we all know, we've been playing various kinds of physical games and board games, starting from Ludo and then going on to cricket ever since our childhood. So we all know what games are. So the games that we focus on, for today, are going to be games that you can play with on a piece of paper and perhaps with a couple of pens. So it's going to be a board game or an indoor game. All right. So I don't know if this game has a name. So let's just call it the game. And then what are the rules? You start with endpoints. So just take a sheet of white paper, put endpoints on the sheet. Instead of calling them points, I'll be calling them vertices. Okay, and you'll soon see why, because this nomenclature is going to gather speed, and we're going to enter into the realm of graph theory very soon. But we'll just call them vertices. No harm. And this is a two-player game. So you have two players, R and B. R for red, B for blue, and so obviously the first player is going to be R or red, and the second player is going to be B or blue. And that, so what are their jobs? So while playing this game, what you do is players take turn in connecting pairs of vertices. So if you have two vertices and it's not connected by a segment, whichever player's turn it is, say blue basically joins these two vertices by a segment drawn using blue ink, for example, or using a blue pen. Okay, and so the crucial thing is, if a pair of vertices has already been connected by a segment, which we'll call an edge from now on, so we'll not call it a segment, we'll just call it an edge. So if a pair of vertices has already been connected by an edge of any color, doesn't matter, you cannot draw another segment or another edge joining the same two pair of vertices. Okay, so if path is there between two vertices, then you cannot draw another path joining the same two vertices. That's one constraint of the rule. Yeah, so a new edge cannot be drawn on a new segment connecting the pair cannot be drawn. And while drawing, two edges can intersect. There's no restrictions on the red edge cannot intersect a blue edge, or a red edge cannot intersect a erstwhile drawn red edge. Edges can intersect, but the point is, we'll not consider the intersection of two edges to be a new point or a new vertex. You should imagine that instead of playing it on a piece of paper, you're playing it in R3, in the 3 space. If somebody has drawn a path and your path is intersecting that path, just imagine it's like a highway that you're just going over or under the actual path, and you're never intersecting the original path that you already had. Okay, so just think of it that way. Because we're drawing this on a piece of paper, you often have to intersect paths because there's not enough room in 2 dimensions. But it's an abstract thing, so we're just like supplanting a lot of these ideas onto a piece of paper for convenience. But the game is an abstract one, and the structures are also abstract. So the intersection, even if we draw an intersection, it's not going to be treated as a new point or a new vertex. The number of vertices are the same that you start with. And of course, it's important that if there is a valid move, a player has to play. Meaning, if there is a pair of vertices which is not connected by any edge, then whichever player's turn it is, he has to draw an edge joining those two vertices of his or her own color. Okay. You cannot say I'll not play this move. Okay, fine. These are the rules. So what's the aim? So the aim is pretty simple actually. The aim is to basically ensure that your opponent ends up drawing a monochromatic triangle in his or her own color. Meaning, if you are the red player, your job is to connect edges using red colors in such a way such that the blue player ends up drawing a blue triangle. And a blue triangle simply means it will be 3 blue edges joining 3 vertices so that it resembles a triangle. Okay. Yeah. Any questions? So we'll draw pictures very soon. Okay. So yeah, the aim is if there is a monochromatic triangle in your opponent's color, then you win. Meaning, if you're the blue player, for instance, your aim is to make these moves in such a way that the red player is forced to create a red triangle, in which case the red player loses, and hence by virtue of that you win. Okay. So that's the aim. So not you create a monochromatic triangle in your own color, but you have to force your opponent to create a monochromatic triangle or a triangle in their opponent's color. So that's what monochromatic means, that a triangle is a triangle and all the 3 edges or all the 3 line segments have the same color, but the color has to be your opponent's color for you to win. So yeah, so before we go on to this thing, so just to make sure people have understood what we're talking about. So let's say we have, so if I play this game on 2 vertices, so n equal to 2, right? This is not very interesting, right? So what would happen if n equal to 2? So let's say the red player is the first player. The red player has to make a move, and so you could draw something like this. You could say, I don't like simple curves. You could draw something like this. Doesn't matter. See, the point is, you have to think of this as an abstract pathway between this and this. So even if this intersects, this is abstractly is just a path. Okay. But the point is, whenever the red player draws a path, the blue player has no more moves left, right? Because the blue player simply cannot play anything, because it cannot draw a blue edge here anymore, because there's already an edge joining these 2 points. So the blue player has no move. So this is not even a 2-player game. It's just like a solitaire game, and it's not even that interesting or fun. Okay. Okay. So what about n equal to 3 then? What happens? Sorry. So we have 3 vertices, and so the red player has to make a first move, and it doesn't matter. You just let's say make this choice, right? So what can the blue player do? The blue player cannot join these 2 vertices, so basically has to do something like this. And it doesn't matter whether you choose this or this, they're symmetric. And then the red player simply has only one choice left, which is this. And that's it. Every game looks like this. So this is also very boring because it's a draw. Nobody wins because clearly nobody can have a triangle in their own color, even if they tried, because there's only 3 edges. And to have one player having 3 edges, that means one player must have played 3 moves, but that cannot simply happen. A player can only get at most 2 moves, right? The first player gets 2, the second player gets 1. So this is also not very interesting. So are there any questions about the setup for n equal to 2 and 3? Okay. If there are, just feel free to ask me. Okay. So what about n equal to 4? That's slightly more interesting, because you see what happens in n equal to 4 is that I'll just draw an abstract thing. So let's just draw n equal to 4 here. So I'm not going to color the edges, but deep in your mind, you already know what these edges are, right? So the point is, whenever I'm talking about n equal to 4, you implicitly imagine that these edges are already there, just that they are not colored. And when you're playing a move, all you're doing is you're coloring these edges, as if this was drawn by a pencil by somebody, and then you're just, like running your pen over it of your own color. So this is technically what is already there at the background. You just don't see it, but it's there. Okay. Something like this. I'm just drawing it this way, but again, my point is, instead of drawing it this way, I could have also imagined drawing it this way. And this is not going to be considered an intersection point. So the best way to think of this is think of this as an overpass or an underpass, or this happening in R3. Since we're drawing it on the plane, these two necessarily will intersect if I draw it this way. So one way to avoid it is to draw it on the outside, or think of this as an overcrossing, undercrossing. But this is not really an intersection in the abstract sense. So this is the underlying board on which the game is being played, and then the point is every player colors one of these edges or pathways red or blue, and the aim is to ensure that your opponent gets a blue triangle or your opponent gets a red triangle, and if it happens, then you win. Okay, so let's see some configurations for n equal to 4. What happens? So this is what happens. Okay, so if you really play obviously smartly and so on for n equal to 4, so how many pathways or edges are there, or how many moves are there? See, there are 6 moves, because between any two vertices there is exactly one pathway or one edge, so it's 4c2. I hope people have seen permutations, combinations. So 4 choose 2 is 6, and you can even count that it's 6 here. And so each player gets 3 moves, right? Red gets 3 and the blue gets 3. So if you're playing correctly, then this would be one particular endgame, that red creates a Z and blue creates a Z, and none of them win. It's a draw. In this case, red creates a Z and blue creates something else, whatever this thing. My point is these two configurations are the same. Okay, so just because I drawn it this way doesn't mean that they're different. These two are the same, because all I'm saying is, instead of thinking of this drawn in this intersecting manner, think of this as an underpass or an overpass, or simply think of this as a pathway which is going around and joining the same 2 points. Okay? So these two are the same end games. This is, however, different, and this is where one of the player loses, right? So which player loses here? Can somebody tell me?
Blue loses.
Yeah. So blue loses, so which means the first player, red, somehow managed to outwit blue and win, because red is the first player. And in this case, you can see that no player wins, because the blue thing. Okay, the point again is, this is not a vertex, so this is not a triangle. Okay, blue is this. Okay, so blue literally sort of looks like this. Blue looks like this, right? And red is that. So none of them form a triangle. So this is also a draw, and this is typically the only configuration which will result in a loss for one of the players. All right. So this is what happens for n equal to 4.
Does this configuration, the third one, also occur if blue plays optimally?
Well, so as you'll see that if everybody is playing optimally, the third configuration will typically never occur, right? So we'll discuss that in the next slide, in the very next slide. So for n equal to 4, if everybody is playing smartly, then the game should end in a draw. Okay, and we'll discuss that. Yeah. So 3 ideally should not occur unless you're making some judgmental error, or you're just having a bad day and you just slip. It should be a draw. So typically it should be either the first configuration or the fourth, or any other draw configuration. But third will typically not occur if 2 smart players are playing at their best capabilities. Yeah. Yeah. Any other questions?
Yes, sir. I have a question.
Yeah.
Suppose one of the players joins the 3 vertices of a triangle, but not with straight line. Then does he win or lose?
No. So the line, see, the straight line is just for convenience that we are drawing it like this. So you could also imagine doing something like this. That's what I said. That a segment is just a segment, right? So the point is just a second. So the point is something like a game could also look like this. Okay. So I'm just drawing it for simplicity, but so blue could be drawing something like this also, right? So blue, this could be a pathway. This could be a path. Sorry, not this. This could be a pathway for blue. Okay, and red could be something very bad as like this. This is all fine. The point is, when I say a red triangle, what do I mean? So a red triangle simply means that it should ideally be, okay, so if somehow red plays something like this, okay, so let's say red played something like this. This is a red triangle because it's this, this, and this, right? So an abstract red triangle. It's a shape which has three edges which can be moved around cyclically. So this is a red triangle, although it doesn't look like a red triangle in the standard sense. Is that clear?
It is clear.
Yeah. Yeah. So I'm just drawing straight lines because it's convenient. But as you see that even straight lines, if I draw like in the first picture, it has an intersection. So you might psychologically not like intersection, although you understand that it's an overcrossing and undercrossing. So you might want to bend the curve and draw it this way. But we'll soon see that bending and twisting curves will not always help. You will run into intersections no matter what you do. So you might as well live with straight line edges and live with intersections. Okay. Yeah. But the intersections are not going to create new points. You have to pretend that this is like an overcross and undercross, or like a highway running over another highway. So you just have to mentally imagine that happening in R3, for example. But you cannot do it on a piece of paper for obvious reasons. All right. Any other questions before I discuss the strategy for n equal to 4, which is pretty simple, but let's go through it step by step, since it was asked by one of you. Okay, so I'm claiming that for n equal to 4, a perfectly played game by both players should be a draw. Why? So what's the non-losing strategy for the first player? So the first player is R, n equal to 4. So it's clear that when can a player lose? A player can lose only when he has completed a monochromatic triangle in his or her own color, which means to lose, a player must have played 3 moves at least, correct? Which means after round 2, both players have played 2 moves and no player could have lost after round 2 because you couldn't have completed a triangle built out of 2 edges or 2 pathways, correct? So no player would have lost after playing 2 moves each. So now what do you do? In the third move, you see, red has already played 2 moves. These 2 edges could be connected. No, so the point is these 2 edges. So here, for example, doesn't matter what blue played. Okay, so red. This is sort of typically what will happen. Red could have played something like this and this. Okay, blue could have played whatever. We don't care at this point. Or red could have played something like this and this. Okay, and like 2 of the other edges are colored blue and 2 of the other edges are colored blue. So now red has to play his last and final move. So here, clearly red can play any move. You will never get a red triangle. Here, there's only one edge which will complete a red triangle. And you know that there are 2 edges left because you have taken 2 into 2, 4 edges have been colored. So there is at least one more edge apart from this one, which is not taken. And you simply color that red, and clearly that will not create a red triangle. So red cannot lose, even in this situation or in this situation, or in the second situation. Is the argument okay with everyone?
Yes, sir.
Yeah. So the point is, it's very simple. You basically play, like do whatever you want up to round 2, and then in round 3, if you are in this situation, fine, you just play whatever you want. Or if you're in this situation, you simply don't play this edge. You play anything else. So and you're done. So red cannot lose. Now look at the strategy for the second player, the blue player, right? So yeah, so you just draw the other edge and that's it. Okay. So whenever R plays the first move, what B does is mimic the move by drawing the opposite edge or coloring the opposite edge. And what do I mean by the opposite edge? So any guesses as to what the opposite edge might mean? So let me just draw out a picture. So suppose I have this thing, right? So let's say red played this one, right? So what would the opposite edge to this be? What would be your guess?
So the remaining 2 points, vertical line joining.
Vertical line, yeah, vertical line here. Okay, and so if I do something like say this, and this, and this, and then let's say I do the red to be this, what should be the opposite of this?
The other diagonal.
Yeah, the diagonal.
The other diagonal. I'll just draw it as an undercrossing, but you guys, all of you realize by now that undercrossing, overcrossing, we know how to separate, and it's just a choice. So from now on, we'll draw them as intersecting things without worrying about this intersecting point being a vertex, because it's not. and we have established that. Okay? Right. So this is what I mean by the opposite edge. So whenever red plays this edge, you play the corresponding opposite edge, and you know what to play. Okay. Now in the second move, R has to draw an edge. Now remember, in both these cases, R has to draw an edge, right? So what will R draw here? No matter what R draws, R cannot draw this because that's taken. So any edge that R draws must connect this blue edge, because R cannot draw this. R cannot draw this. So any edge that R draws, no matter this one, okay, or this one, no matter what R draws, it will be an edge connecting the existing blue edge, right? So this is one particular example. This is another one here, for instance. This could be another one, and so on, right? I'm just giving an example. So now what will happen is, you see, what should blue play? So what should blue play is, so any guesses what should blue play as a second move? To ensure that he will never lose, he or she will never lose. So even though the third move is not.
So he will just join the first A1, B1 and red one. That the upper and the lower.
Yeah, this one, right?
Yes,
okay.
Yes.
And so what will he do here?
There he will join the upper two vertices.
Okay, and what about here?
The bottom two one.
Bottom two, yeah. So formally, what are we doing? What is the strategy for B? So yes, correct. What you said is correct.
Newly drawn red edge.
Yeah, so basically you will try to complete a triangle, but the triangle will have two blue edges and one red edges. So you already have one blue edge and you have a newly drawn red edge which connects to the originally drawn blue edge, and now there's a unique edge which will complete this to a triangle. You color that blue, right? That's precisely what you do. You draw the unique edge that creates a 2 blue 1 red triangle, and now it's pretty clear that blue can never lose, because the only way blue could have created a triangle was by creating a blue triangle, but now blue can never create a blue triangle because the other two edges already is part of a triangle, right? And the third edge, no matter what you do, can never complete a blue triangle. Is that fine? So B can never lose and A can never, R can never lose. So if both play perfectly, the game should end in a draw. Okay. All right. Any questions or clarifications? Okay. So that's it. So n equal to 4 was not that bad, but it's not that interesting either. You know, basically you play a couple of times, you know what you're doing, and you just lose interest. So what about n equal to 5? Let's play a little game. So let me, and here I'll not play. I'll be the one labeling the edges as red, blue, whatever. You will be the one sort of telling me what to do. Okay. So just 1 second before I switch. Yeah, just give me 1 second. I'll just share another tab that I want to share. So is this visible to everyone?
Yes, sir.
So this is supposed to be a grid with a lot of dots and so on. Okay. So hopefully all of you can see the dots, right? So each one of them represent a pentagon. So are the numbers, legible, readable? 1, 2, 3, 4, 5. Are they too small? I can zoom it up if it's too small.
Yes, sir.
Yeah. So the point is, I have labeled the vertices 1, 2, 3, 4, and 5, and we're going to play the same game on n equal to 5. So one of you or a couple of you can play for red, and the other team will play for blue. So before we begin, how many moves should red and blue have typically in this game?
Say 5c2.
Yeah, so 5c2 is the total number of moves, which means half of it. So what is 5c2?
10.
So it's 10, right? So 5c2 is 10. So each player should ideally have 5 moves, at least 5 moves if none of them, like loses before that. right? Okay. So maybe somebody can play for the red team. So the red team can tell me what should be. Remember, the aim is you're trying to win, and blue is also trying to win, and both of you have 5 moves typically. So the red team should tell me what is an edge that I should draw, and you should tell me, for example, 1, 2, and then I know what to draw because it's labeled by 1, 2, 3, 4, 5 in a counterclockwise manner. So yeah, like a couple of you can just team up and call yourself the red team. Hopefully it's consistent and you don't play for both teams because I cannot see. But somebody from the red team tell me which edge shall I draw?
Just 1 and 2.
1 and 2. Okay, very good. So let me draw 1 and 2. Okay, just a second. Yeah. Okay, so now blue team, what shall I draw?
2 and 3.
2 and 3. Okay, so let me just change it to blue. 2 and 3. All right. Now red team again.
1 and 3.
1 and 3. Okay, so you want to basically join this one to this one. Okay, very good. So now what about you, blue team?
3 and 4.
You want to go 3 and 4, this one. Okay, good. All right, now red.
1 and 4.
1 and 4. Okay, so I see. So you're trying to do this spoke business. Okay. All right. So what about blue again?
5 and 2.
Huh? So yeah, one of you at a time, please. So I heard 5 and something. I don't know. Maybe 2 of you overlapped.
5 and 2.
5 and 2. Okay, fine, sure. So let's do 5 and 2. So here you go, 5 and 2. So now we have to give a combination for red, right? So what do you suggest?
1, 5.
1, 5. Okay. Yeah. So red seemingly has some sort of a semblance of a strategy that you just draw the spokes of a wheel, so to speak. Okay. So now what about blue?
Yeah, 4 and 5.
4 and 5. Okay. So blue says 4 and 5. That's probably helping out red slightly. But now what about red? Do you have a move where you will not lose?
Yes, I think red will lose in the next move, no matter what it plays.
So what are the moves left? See, you can do 5 and 3, but then you lose.
3,
You can
5
do,
and 2.
yeah, 3, 5 you lose, 2, 4 you lose, and that's it. Those are the only 2 edges left, right? So red loses in this case because, of course, blue will also lose. But the point is, I mean, it doesn't get to that. Once red creates a red triangle, the game ends there. So red loses in this case, no matter what you do, right? Okay, so this so maybe next time red does a better job. So let's try it once more, and then we'll get on to the general scheme of things. So here again it's labeled the same thing: 1, 2, 3, 4, 5. I haven't put the labels, but it's clear: 1, 2, 3, 4, 5 in counterclockwise manner. So let's start with red again. So what should red play this time around?
Anything is
3 and
1,
4.
2.
3 and 4. Okay. So do you guys realize that the first move, no matter which 2 points you join, the first move is pretty much the same, right? Because any point can be permuted to any other point. Because every point will look as similar or as good as any other point. Because every point has 4 edges emanating from it. And so whether you choose a long diagonal or a common thing, it doesn't matter. So you're saying 3 and 4. Oh, fine. So I'll make that choice for you. Okay. Now what about blue?
So 1 and 2.
1 and 2. Oh, so you're just completely going in the disjoint direction. Fine. So you'll say you go 1 and 2. All right, we do that. Now, what about red? What do you say?
2 and 3.
2 and 3. So, okay, you're connecting up with the blue edge, right?
Yes, yes.
Basically, you're saying I'll just go there and connect up. Fine. All right. So what about blue now? What do you want to do?
2 and 4.
2 and 4. So you want to so you basically are in some sense helping out red by basically completing a potential red triangle to a non-red triangle. That's okay. That's okay. Now, what about red?
2 and 5.
2 and 5. Okay. So which is the horizontal one. I see. All right. Now, what about blue?
So 4 and 5.
No, say that again. 4 and 5. Or
Yeah.
what did you say? 4 and 5. Oh, so you mean you are doing this one? 4 and 5. I see. Okay, fine. I mean, so far so good. See, until you get to like the fourth stage or something, until the third stage, pretty much everything is okay. I mean, nothing much will happen. So what about red? So you have two crucial moves to make.
1 and 5.
1 and 5. This seems like you are on the right track. So what about blue now? What should blue do?
So 1 and 3.
1 and 3. So you are going basically here, right? This one, right?
Yes.
Okay, now see, what should red play now?
5 and 3.
Yeah, so red basically has two options here, but it's pretty clear that what you want is you basically want to join, you want to play 5 and 3. No, you want to play 5 and 3, but then you lose, right?
Oh, sorry.
So you don't want to play 5 and 3. The 5 and 3 is one option, but that is not the viable option if you want to win, of course. So you only have one other option left, right? Namely this one.
It's 1 and 4.
1 and 4. And 1 and 4 is fine because 1 and 4 does not create a red triangle, right? See, all it's creating is a twisted pentagon because it's this, 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 and this. So the red thing is entirely a pentagon. Okay? So now blue has to play the only move left. And does blue win or blue lose? Or it's a draw?
Yes, it's a draw.
It's a draw. So if you see here, what happens is blue also gets this one. And if you look through it properly, the red, when you, so I colored one of the things wrong. Sorry. I think one of the, so this one was supposed to be, sorry. Yeah, so I think my apologies. I think this one was supposed to be red, right?
Yes, that is what I was just getting confused.
Yeah, no,
already a triangle.
No. This one is supposed to be red because I'm doing it in this interface. It's so if you look at the red one, it's a pentagon. You just have to untwist one of the sides, and if you look at the blue one, what kind of shape does it create? So you have this edge, followed by this edge, followed by this edge, followed by this edge, followed by it's also a pentagon. You have to just imagine like an envelope. You take this and you lift it over, and so the blue creates a pentagon, the red creates a pentagon, but they're sort of twisted, and it's a draw because none of them clearly contain a triangle. Okay. All right. So, and you can play this with your friend or with anybody who's interested. You don't need to know any math or any science or anything serious to play this, and you can simulate this enough number of times and see what is happening and come up with your own conclusions. Okay, so I'll not continue playing this because we have to get to other interesting things along the same lines. But are there any questions with this? Okay.
Sir, does there any winning strategy exist in the game?
Okay, so we'll discuss that. We'll talk about general N as well. So we'll get to that. Yeah, sure. So okay. So let me get back to my thing that I was sharing. Yeah. So if you play this enough number of times for n equal to 5, one of the things you'll notice, and I really will encourage you to go back and try this. One of the things you'll notice is that the only drawn configuration is either looking like this or it looks like this. We already saw this appear. Okay, this can also be a drawn configuration because it clearly the blue thing is a pentagon clearly, and the red thing is a pentagonal star. That's how we learn to draw a pentagonal star in high school, right? So both of these are drawn configurations, but I'm saying that these are the same drawn configurations. Why? Because all I can do is I can take the first configuration and I can switch the 3 and the 4. Just remember, just like swapping 3 and 4. If I swap 3 and 4, you get precisely this configuration where the red thing now looks like a 5-pointed star, and and because I swapped 3 and 4, the blue thing now actually becomes a regular pentagon. So essentially they are the same configuration. So there's only one drawn configuration. It looks different, but up to permutation of the vertices, there's only one drawn configuration. So the point is, if two players are playing correctly and so on, and if you know that they will end in a draw, it has to basically look like, up to a permutation, of a version of the 5-pointed star bounded by a pentagon. Okay, so let's go on to the interesting part of the story, which is n equal to 6. So all this is fine. You can play these things. It's often called a pencil and paper game, or a game for children. But what happens for n equal to 6? So when you play on n equal to 6, it turns out this is actually much more interesting than what happens for n equal to 4 or n equal to 5. And this game is called Sim.
Yes.
It's not. Yes.
Here you are bound to have a winner.
Yeah, yeah, exactly. We'll get to that, right? Exactly. That is the starting point. Essentially, now we are getting into the starting part of the talk. So this game is called Sim, and it's not to be confused with the Sims or any other, like simulation game. So this was named after Gustavus Simons, who invented this in 1969. And there are plenty of online free softwares where you can play against a computer. And so basically, you're playing on 6 vertices, and so how many edges do you have? 6 choose 2, right? And what is 6 choose 2? It's 6 into 5 by 2, which is 30 by 2, which is 15, which means the red player typically gets to play 8 moves. The blue player typically gets to play 7 moves, right? So you might suspect that maybe the second player has a better chance of winning simply because he has to play 1 less move. Okay, just let's say by naive introspection. Because the red player just has to play 1 more move in general. So, I mean, your chances of creating a red triangle simply increases. Right? Okay. So, what I would suggest is, like we did here, you just try playing this game with your friends. Some of you may have seen this game, some of you may have not. If you haven't, this is quite fun initially. Play this with your friends a few times online, or even, just share a screen and then play online, for example, and see what happens. Okay. And this is an exercise that you have to do, and I'll fast forward. Imagine just you have done the exercise. I'll fast forward. So the question is, does the first player win more often or the second player? Okay? And as you might expect, that the second player typically tends to win more often. I mean, one reason being he or she has to play 1 less move. Okay? So here's the first theorem: the game of Sim cannot end in a tie. Meaning it has to end with a winner. Either the first player wins or the second player wins, but it cannot end in a draw. No matter how you play it, smartly, stupidly, or erratically, it cannot end in a tie. So we'll give a proof of this, but we'll prove a more general version of another result in the context of graph theory. So we haven't defined graph yet, and then that will imply this result. Okay. So that's why this game was interesting. That you play this game, it's a binary, it's a 2-player game, and it's a binary game. That it has a 1-0-0-1. It's not half. Okay. So, and an important sort of remark here is that computer search has shown that the second player in Sim actually has a perfect strategy for winning. However, this strategy is so complicated that it's perhaps impossible for a human to memorize it and play perfectly. But there is a perfect strategy for the second player. So if you were a computer sort of in your mind, and you know this perfect strategy memorized down to the T, then you would win whenever you're playing as a second player. But practically speaking, this doesn't happen that way. Okay. So if you play and you're not very careful and you're the second player, it might end in you might end up losing, right? So all right. So we'll give a proof of this, but we'll prove another result which is slightly more general, and that has a very easy proof, and that will imply this proof. So why that implies this theorem, I'll initially leave it as an exercise. We can even discuss it later. So that's the statement, that n equal to 6, the game of Sim always has a winner. All right. So now let me take a small digression into what is a graph, because we are talking about these things, so it makes sense to just introduce them anyway, because there's no point calling them vertices and edges without telling you what we're dealing with. So what is a graph? A graph G is basically, capital G for graph. Sometimes they use capital gamma, because gamma is the Greek or alternate for G. Anyway, we'll use G. G is a pair of sets, V comma E. So V is going to be the collection of vertices. So it's a set. I'm going to call it the set of vertices. And E is going to be the set of edges. So typically, when you write down E, you should think of E as a subset of V cross V, because given two vertices V1, V2, if there is an edge joining V1 to V2, I indicate that information by simply saying that my edge set E contains the element V1, V2, the pair V1, V2. And I don't distinguish between V2, V1 and V1, V2 because my edges don't have direction. My edges are undirected. So if there's an edge joining V1 to V2, the same edge will serve as an edge joining V2 to V1. So I typically one thinks of E as a subset of V cross V. Okay, I hope that is clear. So if I have an E which is a subset of V cross V, I look at an element in E, it's of the form V1, V2. That tells me that there is an edge joining V1 to V2. And if E does not contain V1, V2, that means there is no edge joining V1 to V2 in my graph or in my pictorial depiction of the graph. Okay. Yes, any questions or clarifications? So we'll see some examples. Okay. So here are three examples. I'm just calling them planar realizations of some graph, but I'll put realizations within quotes. So this is a graph, the first one. It has four vertices, right? And it's just what it is. It's basically a triangle, and then there's a one extra arm sticking out. Okay. If you look at the last one is a triangle. There's an arm sticking out, and then there's a lasso, and there's one extra isolated vertex which is not connected to anything else. So this is also a graph. If you label the vertices 1, 2, 3, 4, 5, then you can label the edges as 1, 2, 2, 3, 1, 3. And then this one has no edges. So if this vertex is level 4, then in the edge set, you will have nothing of the form 4, something or something, 4, because there's no edge joining 4 to anything. And this edge, if this vertex was level 5, this edge would be level 5, 5, because it's joining 5 to itself. It's a self loop. So in usual graph theory, you don't deal with such things, but in the general context of graphs, you do deal with such things. And in fact, these things are very important in physics. When they talk about this like Feynman diagrams and then this loop integrals and so on. So a general graph will admit these kind of edges as well, self loops. It can have multiple edges between the same two vertices. I'm not ruling that out. So yeah, so you can have one edge joining these two vertices. You can have another one. So a graph allows that to happen. Typically, you call it a multi-graph if that happens. Since we are dealing with standard graphs, we'll not get into that discussion. It can also have isolated vertices, which have nothing to do with the rest of the graph, but it's still part of the vertex set, so it's still part of the graph. So these two are nice in the sense that you can faithfully represent the abstract data in the plane itself. This one is not nice in the sense that we discussed at the very beginning, that this intersection is not really there. Okay, it's just there because we are trying to draw it on the plane. This is not really an intersection. This is an undercrossing, overcrossing. Same here. This is not an intersection. And same here, this is not an intersection. Okay? But modulo that, this is a graph on 5 vertices, and you see that this is a multi-graph because there are 2 edges joining this vertex to this vertex. Right? Okay. Any questions or any clarifications regarding the definitions?
So what's on the rightmost figure? Is it an overcrossing?
Which one? This one?
Yes, sir. Yes, sir.
No, it's not an overcrossing. So this is just a loop starting and ending at this vertex. So think of it as a pathway, just starts and ends at. It's like a lap in a field, for example.
So what will be the graph at that point?
No, so the graph is literally the vertex set is 1, 2, 3, 4, 5. So if I draw it out, the vertex set is going to be, if I call this 5, for example. Sorry, let me just change the. Yes, so if I call this 5, call this 4, call this 3, call this 2, call this 1. So the vertex set is basically 1, dot 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 comma 5, right? What is the edge set? The edge set again, basically it's symmetric. So if I put 1 2, I'm going to put 2 1 because 1 2 is 2 1. I'm going to assume that. So you see 2 3 is there, right? And similarly 3 2 and 2 3 are the same because it's undirected. 3 4 is there, right? And 2 4 is there, correct?
Yes, sir. Yes, sir.
And you also have 5 5, right? But you have nothing else because 1 is not connected to anything else. And you also have 4 5. Sorry, you also have 4 5. Correct? That's the edge set. Okay. So if you have, so now you can ask, fine, we can get away with this thing. But suppose I had one more loop, then what do I do? Well, then that's where you have to enlarge this concept to what's called a multigraph. So you have to allow multiple occurrences of the same element. So a set cannot have the same element appearing twice, but in multi-sets you allow the same element to occur twice. So the fact that 5 5 occurs twice means that there are two self loops. One of them corresponds to one of them, the other one corresponds to the other. Okay? That would be a slight sort of nuance into the whole notation. So you call them multigraphs and you study them as well. But so this is already a multigraph because you have two edges joining the vertex 2 to vertex 3. You'll have the element 2 3 appearing twice in the edge set E. So E is actually going to be a multi-set where you're allowing repetition of elements. But yeah, but anyway, in our case, we don't have this because we don't, I mean, in this example, this is the set. Okay. With up to symmetry, you can throw in 3 2 or declare 3 2 to be equal to 2 3. And so then these are the 5 edges. Is that okay?
Yes, sir.
Yeah. Are there any other questions or clarifications? We're just going to need the language. We're not going to talk much about graphs, but the language is so well established at this point that it's essentially as much a part of math as much as it's a part of part of computer science. So I mean, it might as well know it in the context of the language rather than skirt around the issue and not call a graph a graph. I mean, a graph is what we're talking about, right? So yeah. So among graphs, there are these special graphs which are called complete graphs. And we're going to talk about a complete graph on n vertices. What does that mean? Well, simply there are n vertices, and complete means any two pair of vertices, any two disjoint pair of vertices has an edge connecting them and exactly one edge connecting them. Okay? So we'll denote this by K, capital K subscript n for the number of vertices, and capital K is very traditional for complete graph. Is one where there is a unique edge between any pair of distinct vertices. So what would be a picture of K3, for example? Or let's start with K2. What would K2 look like? Maybe it's just a
line segment.
Yeah, so it's just a line segment. So K2 basically is you have two vertices and then you have to join it by an edge, and that's it. Now what is K3?
A triangle.
A triangle.
Yeah, so K3 you basically have this, and then you have to join each. So you have three edges, this. What is going to be K4?
Quadrilateral with its two diagonals.
Yeah, so now you see that you can probably say I'll do this one, and then I do this one. If you want an intersecting picture, you do the undercrossing, or if you want a non-intersecting picture, you do this one. Okay? So far so good. We can get away by not intersecting things and give a faithful representation of K. That whatever, because two edges don't intersect, they intersect only at the endpoints or at the vertices. So far so good. We have a faithful picture, but you'll realize that if you try to draw K5 on a piece of paper, no matter how ingenious you try or how hard you try, you cannot draw K5 faithfully on a piece of paper, meaning two edges will definitely intersect away from the vertices if you draw it on a piece of paper. And this is a classical result that you'll see in graph theory when you take a course on it, that K5 is not a planar graph. You cannot embed K5 on the piece of paper without ensuring that any two edges don't intersect. I mean, there'll definitely be at least two edges which intersect not at the vertices, but intersect in the sense that we have been talking about, right? They intersect like this. Okay, so these are the few pictures. So the first one, obviously, this is K3, right? This is K4, this is K5, and we already saw this happen in one of the sim game, right? So this is literally where we're coloring. So sim game was you basically You have red color, your friend has blue color, you just color the edges by red, blue, and then whoever wins. And this is K6. Okay, and it's so all of these can be embedded or drawn faithfully on the plane. K5, K6, none of these can be drawn faithfully on the plane. Meaning, no matter how cleverly you draw some of these edges in curved manner and so on, they will self-intersect. At least two of them will self-intersect, starting with K5 through K6, K7, all the way to Kn for any n bigger than or equal to 5. Okay? But they exist as graphs, so you just have to imagine them as undercrossings and overcrossings. So that's what a complete graph is. Okay. Okay. So now we can restate the statement of sim by saying that all we are doing is we're playing a coloring game on this K6, correct? Because the edges are already there. All we are doing is we are taking turns in coloring one of the edges red or blue. So we are really edge coloring the graph in two colors, red and blue. So the question becomes, if you take K6, you edge color this graph in two colors, red and blue, and you do it in any order. You do not have to take turns. You can color all of them red, color all of them blue, color half of them red. You just do it in a random manner. You don't have to follow the rules of the game. So the rules of the game will produce a coloring of the edges into two colors, but you just color K6 using two colors randomly. You get a coloring of K6. The question is, does it have a red triangle or a blue triangle? Because that's practically what determines whether you win or lose, right? So if you can somehow show that no matter what two coloring you do for K6, there is always a blue triangle or a red triangle, that means that corresponding player loses. Is the setup clear? Okay. Any questions? Okay. So yeah, so this is the question translated in the form of graph theory, that you take a two coloring of the edges of any graph, in general K6. That simply means you are assigning to every edge of K6 one of the two possible choices, red or blue, and you do it practically in any manner that you wish. You do not have to take turns. You can color it. You can two color the edges by yourself. You don't need a friend, right? The point is, you get lots of configurations. A priori, say how many edges are there? There are 15 edges, right? And each edge can be given two possible colors, correct? So a priori, if you just don't take any symmetries into consideration, there's 2 raised to 15 many configurations in terms of coloring. That's a large quantity. Of course, there are symmetries which will cut it down, but still a huge number of colorings. I mean, it's not really any small number. So the question is, among all those colorings, can we always say that every two coloring of K6 always has a monochromatic triangle, meaning either it has a blue triangle or it has a red triangle? If you can prove that, then that definitely, with a little bit of thought, will help you prove that the game of sim must have a winner and hence must have a loser. Yeah, any questions? I think somebody, audio. Okay, so the proof is very simple. Okay, so the proof is, imagine you take the palm of your hand. Okay, so you need 6 vertices. Where are the 6 vertices? Well, the tips of your, your fingertips, 1, 2, 3, 4, 5, and then this thing here. Okay, so if you have seen Kill Bill, for example, there's this 5-point palm exploding heart technique. So this is not quite as devastating as that, but it's still nice. So you have these 5 fingertips, and then you have this point. So you have 6 vertices, and you have colored them.
You will get 2 monochromatic triangles.
No. What's the question?
Is it more general that we can also find 2 monochromatic triangles can be found as well?
No, 2 might happen in some cases, but not always. So generally, you will only have one monochromatic triangle in red if everything is going according to plan. In a general coloring, sure, you might have lots of red triangles, lots of blue triangles. Why not? But the point is to show that, and there are configurations where there's only one, where there's monochromatic triangle in red and none in blue, or in blue and none in red. I mean, depending on which color you choose, right? So, but the point is to show that there is at least one monochromatic triangle, either in red or in blue. So here, if I choose these 5 vertices and then I choose this, now see, the point is, if I fix this vertex, I have 5 edges, right? So ignore the gray edges. I have 5 edges joining the fingertips, 1, 2, to the middle finger, the index finger, and then the thumb. So I have 5 edges and I have to color them using red or blue. So I can use pigeonhole principle, right? So I have 5 edges, I'm coloring them red or blue. So at least 3 of the edges will have the same color. At least 3 of them, right? Maybe all 5 of them are colored red. I don't care. At least 3 of them will have the same color. Let's assume that this color is red. If it's blue, then the argument is practically the same. So let's assume that at least 3 of these edges joining this particular point to any of the 5 fingertips is red. So let's say these 3 edges are the little finger, the ring finger and the middle finger, right? So now you focus on these 3 vertices. What happens here? So you still have to color this gray triangle, right? Now what can you do? Well, if you color any one of these gray edges by red, you have a red triangle. So you have a monochromatic triangle. So if you insist that I'll not color any one of the gray edges by red, what is the only option left?
We have to color all of them with blue.
By blue. So then you get a blue triangle, right? So the proof is as simple as that, and it's a proof that some of you may have seen it. If you haven't seen it, it's a proof that you can sort of take with you for the rest of your life. It's really simple, really elegant, really easy, and you can explain it in a party with just like a wave of your hand, so to speak. You don't need any technique or anything. Okay. So yeah, so here's the theorem that any 2 coloring of edges of K6 contains either a red K3, a K3 is nothing but a triangle, or a blue K3. It might contain both, but in some instances it doesn't contain both. We only care about existence of one monochromatic triangle, whichever color doesn't matter, and that is ensured by this. Okay. So this was.
Can you give an example in which we can't find one such? I mean, 2 monochromatic triangles.
Yeah. So why don't I leave that as an exercise for now? You can try coloring and see. So the point is, if the red is the first player playing, you have to basically ensure that just color blue so that blue has to play 7 moves. Just play the 7 moves so that there's no blue triangle, and then color the rest by red. And that's not hard to arrange. Okay. So yeah. So does that answer your question? Okay, so this was popularized by Paul Erdős, whom you may have heard of. He is a very prolific mathematician and a very, very exemplary problem solver. And he has so many quotes attributed to him and so many results named after him. So Paul Erdős popularized this by saying that if you are in a party where everybody so if you take any 2 people in that party, either they know each other, they're mutual friends, or they're sort of mutual strangers. Okay. So they either don't know anyone. So it's assumed to be a symmetric relation. I am a friend of yours typically means that you are a friend of mine as well. Okay, if the friendship is somewhat reasonable. So he's assuming that either 2 people are mutual friends or they're mutual strangers. Then he's saying in a party, pick any 6 people at random. You're bound to find a group of 3 who are mutual friends or a group of 3 who are mutual strangers. So often these KRs are called cliques, because clique is like the usual term for a close-knit group. So it's saying that you'll find a clique of size 3 of friends or a clique of size 3 of strangers. So it's just a more popular interpretation of the same theorem. Okay. All right. Any questions with the proof? Okay. I'll just take like 10 minutes more. I still have, I think, 5 minutes. Is that fine?
Yes, sir. Yes.
Yeah. Okay. So I mean, it's good that people are asking questions and we're discussing, because I think that's more fruitful. So here comes the other hero of the story, which is Ramsey. Okay. So this is Frank Plumpton Ramsey. So what is a Ramsey number? So it's a number. We've been discussing various numbers, like 6 is somewhat crucial, and we saw that you can color K5 in 2 colors where there's no triangle, right? We have seen that. And we said that if you color K6 in 2 colors, there is always a triangle. So somehow there is a critical point where whenever we go from 5 to 6, something changes. So a Ramsey number written as R, like capital R for Ramsey and little r, little b for red and blue for now, but these will be integers. So capital R of R comma b is what? It's by definition the smallest positive integer n, such that whenever I take the complete graph Kn, I color the edges in 2 colors, red and blue. I expect to find at least one Kr in red. Remember what is KR? KR is a complete graph on R vertices. So what I'm asking is, it should be the smallest n such that no matter what two coloring of Kn I choose, I'll be able to find either a complete subgraph KR all colored red or a complete subgraph KB all colored blue. So in our example, we said that R33 is 6. Why? Because if you take any two coloring of K6, it must contain a red K3 or a blue K3. Okay? So R33, and it's not 5 because we saw that in K5 there is a coloring with no red triangle or blue triangle. So R33 is bigger than 5. It is less than or equal to 6 by the theorem, so it is exactly equal to 6. So that's the first kind of Ramsey number that we have already seen. So any questions with the definition? Okay. So of course, it's when Ramsey defined it, he probably didn't call it Ramsey number, but as is the case that it's attributed to him later on down the line. So in 1928, this is almost a century back. So Ramsey proved that these numbers exist. Okay. So okay. But there are certain things you can note. So first of all, what is R2K? I'm saying that R2K is K. So can somebody justify why this is the case in simple terms? So R2K is what? You're looking for the smallest integer n so that you take any two coloring of edges of Kn. It must contain a red edge because a K2 is an edge. It must contain a red edge, or see if it does not contain a red edge, which means all the edges are blue, right? Which means you practically get back Kn. So if you take the complete graph on K vertices, you either color everything blue, in which case you get a blue KK, or you color one of the edges red, in which case you get a K2 in red. So that's why R2K is K. So this is very simple, and hence I didn't want to mention it at the outset, but I hope this is clear to everyone why R2K is K. Okay. Any questions?
How can you replace the number RB with integers like these 2 and K?
No, what happens? Say that again. Sorry. What happens if
R, comma B is the number written after R. So what is so what I am replacing by R? 2 comma K is K. So how can I get that? Please explain to me.
Yeah. So are you asking why is R2 comma K K?
Yes, sir. Yes, sir.
Yeah. So the point is, see, what is R2 comma K? You're saying that it is the smallest integer little n such that you take any complete graph Kn, you color the edges red and blue, right? So if any one of the edges is colored red, you're done because that's a red K2, right? This first two is just saying whether there's a red K2, right? So
yes.
So if red K2 does not exist, that means what? Every edge has to be colored blue because only have two colors, right?
Yes, sir.
The entire graph is now a blue KK, correct? Or KN.
Yes, sir.
So that's why if you take a complete graph on K vertices, it must have K vertices anyway because you want like KK to exist. If you look at the complete graph on K vertices, if your coloring has at least one red edge, then you win. If your coloring has no red edges, even then you win because then everything is blue and it's a blue complete graph, right?
Yes, sir.
So it's just that, yeah. So it's a
okay, sir. Thanks.
Yeah.
Sir,
Yeah.
is there any special name for a Ramsey number in which KR and KB exist in KN?
KR and KB. I don't know if there's a name. See, there's like a whole bunch of literature on this, but as you soon see, like even computing these things is a big challenge. I don't know of a standard name. There might be specific names in the literature. I'm not aware of any, but I don't know if, definitely there's no common name like Ramsey number or multicolor Ramsey number, which is as commonly used as these ones. So you might just have to call it by whatever it is,
Yeah.
Yeah. Okay. And we already talked about this, that R33 is basically 6. So this is the other non-trivial Ramsey number that we have computed so far. So I'll just list out some properties. There are plenty of references when you search for Ramsey theory, Ramsey number, Ramsey coloring. You'll be able to find lots of articles where you can read, and some of these now have pretty readable elementary proofs. So I encourage you to go back and read them. So the first thing is symmetry, and the symmetry is pretty clear because if you have a coloring, you can basically switch the colors. Like given a coloring, whatever was colored red, you make it blue. Whatever was colored blue, make it red, and then you simply switch the KR to KB and KB to KR. So that switching will give you the symmetry that RRB is RBR. This is not a hard thing to visualize, okay? Because you just swap the colors and then the KR and the KB swap, and so RRB is RBR. But this is slightly more non-trivial. This is attributed to Erdős, Paul Erdős, and George Zekiris. So Zekiris, interestingly, was a chemist by training, okay? And then he ended up doing a lot of stuff in combinatorics with Erdős and so on. But he was trained as a chemist. So they proved this bound, that which is not a bad bound, but it's not a very good bound for a lot of things that people would want to do. But it's a bound nonetheless. That RRB is less than or equal to R plus B minus 2 choose R minus 1. So I hope people are familiar with this notation. This is N choose K. So I wrote it in this bracket from. This is R plus B minus 2 choose R minus 1. And you see that R minus, if I replace R minus 1 with B minus 1, it's the same thing. So I can use R minus 1 or B minus 1 in the denominator. This coefficient is the same. So that's an upper bound. And in fact, later on in the mid 50s, Gleason and Greenwood gave a slightly better bound, which is quite useful even to this day. And in fact, you can use this to give a proof of this, which is actually easy using binomial identities and so on. The original proof involved other methods. So this is what Gleason and Greenwood proved, that RRB is less than or equal to the sum of two Ramsey numbers. One is RRB minus 1 plus R minus 1B. So you just downgrade one of the R and the B one at a time, take the two Ramsey numbers, add them. That sum is bounding RRB and from the top, okay? And so here's an exercise for you, for those who are curious and who want to try it out. So this one is not that bad. You can use these inequalities, and maybe you have to play around with some explicit examples to show that it's 9. Okay, so you have to show that it's bigger than 8 by giving a construction on K8 which does not have a K3 or a K4 of red or blue colors. But the 9 you can sort of almost get from this inequality, because you see R34 is less than or equal to R24 plus R33, right? What is R33? 6. What is R24? 4. So from the last inequality, you get R34 is less than or equal to 10. Okay, but you can actually, if you revisit this inequality a little bit, you can show that you can get it down one more. So you can show that this is in fact less than or equal to 9 with a little work. What is left to show here is that R34 is strictly bigger than 8, meaning you have to produce a two coloring of K8 with no red K3 and no blue K4. So is it clear what the exercise entails?
Yes.
So that's an actual construction you have to do, you know. And typically these constructions come about from all sorts of places. Either it's an ingenious construction, or it uses some symmetry, or it uses some ideas from number theory. I mean, it comes from all sorts of places. Okay. And so here's the second part of the exercise, which is slightly harder. But if you're really feeling adventurous and you do the first one, you can give it a try. That R44 is 18. This is definitely not as easy as this one. You have to do a little bit of work, because the upper bound you might somehow get from here and it might match. But then how do you rule out the lower bound? Because you cannot just rule out the lower bound by any kind of estimates like this. You have to literally construct a Kn with a coloring which does not have the right property to say that, oh, it cannot be 16, so it must be 17 and 18. And then you say, oh, it cannot be 17, so it must be 18. And then you prove that it's 18 by using one of these bounds. So it's part of the same exercise, but there's gradation in difficulty. So you can give it a try. But we're actually getting to the heart of the story. So the question is, how much do we know about these Ramsey numbers? Just the two coloring Ramsey numbers. Okay. So they are notoriously hard to compute. They're really, really hard. And you can imagine it's been almost a century. And we know very, very little about tables. For instance, if you ask what is R310, everything up to R39 is known, but R310, it's not known whether it's 40 or 41 or 42. It's known that it's one of the three by using various bounds and various estimates, and then using algorithms to run through various colorings and so on. But you still don't know which one it is. Okay? But this is still probably not as hard in retrospect or conceptually as you can say, okay, what is R55? We know R44 is 18, R33 is 6. What is R55? The diagonal Ramsey numbers. Well, it turns out R55 is between 43 and 48. But we don't know which one it is. Okay. In fact, it was conjectured in 1997 based on work by a few people, largely based on computer simulations and running through swaths of colorings of the canes. They conjectured that R55 should be 43, but nothing is known yet whether it's actually 43, but it's believed that it should be 43. Okay, although approximate or a priori it lies in this range. Okay? And it's also known that R66 is in this interval, but this is quite huge. You see, just because you go from 44 to 55, you get these many things, and you don't know which one it is. And if you go from 55 to 66, there's already 64, numbers to choose from. It goes from 102 to 165. And the worst thing, or the good thing, depending on how you want to look at it, is that the lower bound, 102, has not been improved for almost 55 years. For more than 50 years, people couldn't improve this by saying, oh, it cannot be 102, it has to be 110 at least. I mean, there's no improvement at all. Okay? And the reason might be that if you were to take a crack at this and solve it in your own way, and I'm sure some of you might like to work on similar problems or might find this interesting, and I'm saying this because some of you might actually have the tenacity and talent to make a crack at this. You'll have to come up with techniques outside of graph theory to solve these things. I mean, the typical techniques of graph theory and using computer simulations to analyze colorings will only get you so far. But after a point, the computer power fails, and that's not a feasible way to come up with a theory. So any theory that you come up with to solve this will typically involve other areas of mathematics coming together to help out graph theory in a nice and deep way, perhaps. Okay. So here's the quotation. So regarding how hard it is to compute R55 and R66, here's another famous Paul Erdős story, and I'll just read from what he had narrated, and this has been published in a book and it's well documented. So Erdős was asked about this. So how hard did he think R66 was to compute? And he says, imagine an alien force, vastly more powerful than us, landing on Earth and demanding, for some reason, the value of R55. So this is just a tongue-in-cheek. I mean, why would they ask for the value of R55? You might wonder, but imagine that they simply care about R55 among all things, and they ask you the value of R55, or they'll destroy our planet Earth. In that case, Erdős says that we should immediately marshal all our computers, supercomputers, all our mathematicians, and anybody who can help, and we should attempt to find the value, just collectively and individually. However, he warns you that instead, if the aliens ask you for R66, he says immediately, no questions, start fighting with the aliens in the hope of destroying them, because he believed that there's practically no way one could compute R6. Okay. So anyway, this is to be taken with a bit of tongue-in-cheek, but the point is R66 is really hard, and you can see just going from R44 to R55 is hard. To R66 is stupendously hard, and if you go beyond it's hard not only computationally, it's hard just because there's no theory in place. Okay. All right. So with that, let me finish with what would happen if you generalize this slightly. Okay, and so that it ends on a note. So yeah, any questions?
What kind of techniques can one apply in graph theory other than these combinatorial techniques?
No. So yeah, so the point is, see, there are combinatorial techniques, but then there are techniques from probability. So you look at the collection of all graphs with all colorings, and then you bring in probability, and then use random graphs and techniques from there. And you can say things like, with probability 1, certain event can happen, right? So those are very common techniques that are used these days. But whether it will actually be useful here is a different story. So so you can bring techniques like those, techniques from maybe sort of statistical mechanics and so on, because they also have these kind of like magnets lined up in a lattice, and magnets are aligned in a certain way, and then so that's like a discrete version of what they're trying to study. And so there are techniques that are being used here and there, but you have to somehow find the right technique and see whether it fits in here. And not only does it fit in, whether you are able to compute it with that technique. If you cannot compute, then again it's the same old story. I mean, the point why graph theory couldn't make much progress within itself in this direction is because after a point it became search through all colorings and see if you can make any progress, and then that just goes beyond the computational power because it grows too fast too quickly, right? So, yeah. Any other comments or questions? Okay.
Can you please go back to the K6 part?
Here, this one?
The K6 part, that K6, only one.
Even before?
Yes, that was just before that. Yeah.
This one?
So
yeah.
I am just arguing. So we can we prove using pigeonhole principle that in a K6 graph, each vertex of K6 contains at least 3 edges monochromatic?
Yeah.
Yes. So this implies that in a total in the K6 in the complete K6 graph, there are at least 24 6 times 4 monochromatic angles.
No, wait a minute. So what do you mean monochromatic angles? You mean things like this?
Yeah, with the same angles between two same colored edges.
Right. But you have to. But see, it's not going to be entirely 24 because you're overcounting things also, right?
No, it's greater or equal to 24. I mean.
No, but how are you getting 24 here? That's what I'm not getting.
In every vertex there are at least 3 monochromatic edges.
Sure.
Then there are at least 4 monochromatic angles.
4 monochromatic angles. No, if you have three monochromatic edges, here I can only see sort of.
You can do casework. Like if you have one vertex and from that you have 5 monochromatic edges emanating from that point, then you'll have 5 C2 monochromatic angles. If you have 4 and 1, then you'll have 4 C2, which is.
Yeah, and then here it's 3. Yeah, here
and
is
if you have 3 and 2, then you will have 3 C2 plus 2 C2. That will be 4, and that will be the lowest. So you can either have 4, 6, or 10 monochromatic angles for forming at a single vertex. So considering like worst case, you have at least 24 monochromatic angles.
Yes, that is actually I'm just telling.
Okay. But what do you do with the monochromatic angles?
Yes, there each monochromatic triangle has 3 monochromatic angles.
Yeah.
Now in a K6 graph, there are a total of 6 to 3 triangles, that is 20 triangles.
Yeah.
Now we assume that the number of monochromatic triangles in the K6 graph be x.
Okay.
Then if we have to find, it suffices to find the number of 20 minus x non-monochromatic triangles. There must be 20 minus x non-monochromatic triangles because 20 total triangles and x monochromatic triangles.
Yeah, sure.
So we can putting all these together, we can say that 3x plus 20 minus x is greater or equal to 24.
Okay.
Which gives x greater or equal to 2.
Okay. So you're saying there must be at least 2 monochromatic triangles.
Yes.
Coloring. Yeah. So yeah, that's I guess possible. So the point is, in a typical game where it's played perfectly, what will happen is that there'll be 2 monochromatic sort of red triangles, and the blue will be the winner in the sense that the red plays one more. So what will happen is, in a game where red loses, it could happen that the last edge that you actually are forced to draw will complete 2 triangles at the same time. That can happen. Or it will just complete one, so it will just complete one triangle at that stage, but it already had one triangle. So in which case you might have lost the game anyway. So you wouldn't continue. But for the coloring sake, we're just imagining that you continue the game until you have colored everything. So in a typical game, if you have played badly, you might just stop much earlier. But if you're playing perfectly, you have to typically go all the way. In which case, you might complete 2 triangles at the last stage itself. Yes, that's possible. Yeah, any other questions? Okay, so yeah, so I was saying that this is a very famous quote by Erdős. So we can now generalize this to multicolor Ramsey numbers, which is R, N1, N2, Nk. And what are these? Well, these are simply, you can imagine what they're going to be. This is the smallest n, such that whenever you take a kn, you color the edges of kn in using k colors, C1, C2, Ck. And then what you're saying is the smallest n should be of such a should satisfy this property that any coloring of kn, k little n, with k colors should have at least one kn1 in color C1, or at least one kn2 in color C2, up to at least one knk in color. So one complete graph on n1 vertices in color C1, all the way up to one complete graph in color Ck on nk vertices. At least one of these things should appear in the coloring of kn. Okay? That's what it is. So you can do it with 3, for example. You can say what is 2RB. So my 2 here, I am using a color, but so R of course stands for the color capital R, red. Little b stands for the color capital B. So I am asking whether there's a complete graph of size KB, which is colored blue, or a complete graph of size KR colored red, or a complete graph of size 2 colored green. So this color is associated to green, red, blue. And I'm saying that R2RB is simply RRB. Can you see why? So I'm trying to take a graph, complete graph, color it by 3 colors, green, red, blue. And to have a K2 in green, that simply means I must have one edge which is green in color. Then I'm done. So if none of the edges are green in color, then all the edges are either red or blue, right? So it's practically RRB, isn't it? And if there is one edge which is green, then I win anyway, in which case it's this. So having a 2 is as good as not having anything practically. And we saw that last time as well. R2K was simply K. This in the same line. R2, R, B is nothing but R of R, B. Because either you have a green edge, in which case you're done. If there is no green edge in the coloring, all the edges are red or blue, in which case you are asking for a KR in color red or a KB in color blue. But that's precisely what this is designed to do, right? Okay, so I hope this is clear. Any questions? Okay, yeah. So this is just the argument that if there's a green edge, fine. Otherwise, all edges are either red and blue, and you get a bound, and you can check it. Okay? So you can ask, since we know what it is, if one of them is 2, so might as well start with red, blue, green, but all of them are at least 3, because having one of them to be 2 is not very interesting. I can just go back to the Ramsey number that we defined using 2 colors. So let's assume all of them are at least 3 or more. And you can ask, what is this number? And so does anybody have any guess or anything surprising that you might have, if you have heard, you know it, but any guesses regarding how hard it is to compute this? What would be your guess? Just so that it puts things in perspective. If you haven't seen these things, the first one is R33, right? The next one would be R334 maybe, or R443. So, I mean, when I first heard of this, I was very, very surprised. One can show that R33 is 17. Okay, that one can show. This requires a little bit of work, but one can show it. What is more astonishing is that this is the only known multicolor Ramsey number. meaning there are bounds for all the other ones, but there's no exact value known for any of the other ones. R344, R444, R445, you just name it. And this is only for 3 colors. You can imagine how hard this is going to be for multicolors. There are bounds, there are recursions, but this is the only explicit Ramsey number, multicolor Ramsey number known for red, blue, green. Okay. So again, the point is, maybe one of you will find this interesting, may get inspired by some other piece of mathematics somewhere, make a connection, and then come up with a groundbreaking piece of work to sort of prize open this whole area, and then bring in new tools and techniques, and then maybe we'll see some new mathematics born out of that. Okay. So all right, so instead of explaining why this is 17, let me just end with a picture. So let me tell you why it is not 16. So saying that it's not 16 means what? I should be able to give you 3 coloring of K16 with no triangles in red, blue, or green. Correct? That's what it means to say that it is bigger than 16, and then you have to use some bounds to say that it is less than or equal to 17. So I'll give you a pictorial proof that it's bigger than 16. Okay, are you guys ready? So it's the same graph, but I'm just drawing out in 3 separate portions. So if you see closely, the vertices are labeled V0 through V15. So there are 16 vertices, and the labelings are not matching up exactly here. So this is V11, this is V12, this is V1, this is V2. But I hope it's clear. Okay. So you basically have to superimpose these 3 graphs, but not as given. You have to superimpose the vertices on the vertices. So here, the V1, V2, V3, V4, V5 has to be superimposed with this V1, V2, V3, V4, V5, which has to be superimposed with this V1, V2, V3, V4, V5. Okay. So if you do the superimposition carefully, you'll get a 3 coloring of K16. This is clearly K16, and you can check each of the red subgraphs, the blue subgraph, or the green subgraphs, that there's no triangle in red, or a triangle in blue, or a triangle in green. I mean, that's something you can visually check, and every edge is accounted for. And so this is something which you might say, okay, how does one come up with this? Well, you have to use some symmetry, sometimes use ideas like quadratic residues from number theory and so on, but it exists. So it is not 16. So then the question is, how do I know it is less than or equal to 17? Well, that's an algebraic bound. You have to bring in other techniques, but that is known. The fact that R33 is 17 is known, and it's celebrated because that's the only known multicolor Ramsey number. So with that, I'll end. Thank you for your attention.
Sir, I have a question.
Sure.
Sir, in all 3 graphs are the same and they're colored with 1 color only, right?
All 3 graphs are the same. No. They're not the same. As I said, see, you have to look at the vertices. So can you read the vertices, or you probably cannot? So let me just zoom it up a bit, okay? Let me just zoom in. Can you now see?
The vertices number are changed.
Yeah. So that's what I said. It's very critical. So I hope you can see. Yeah. So there's one small typo here. So I think these 2 are correct. This one, the V, yeah, this should be a typo. This is a typo, definitely. So this should be V. Well, 1, 2, 3, 4, 6, 7, 8, 11, 12, 15. Oh no, it's fine. It's fine. So you see that the V11 is appearing twice, but appearing twice, I'm drawing it in this way because this vertex is identified to this vertex. So you have to basically wrap it around. I'm drawing it for convenience. So this V11 is the same V11, but this side I have V11s through V15. That is not the same as V11s through V15 here. This is V1 through V5. Are the indices visible to everyone? Or is it too small?
Yes, sir.
Yeah. So you have to, as I said, you have to take care. I mean, the graphs look the same, but the point is I have interchanged the vertices. So first of all, this has to be identified to this. V12 has to be identified to that, and then you get a red graph, but that has to be superimposed with the corresponding blue graph where this V1 is identified to V1. So this V11 is going to be identified with this V11, which is going to get identified to this V11 over here. So is that clear?
So, sir, in this shape, we can assure that there is no such triangle.
Yeah, that you can sort of almost detect by looking at either one of the graphs, because all the graphs as they're drawn are essentially the same up to a releveling of the vertices, and you could check any one of them, show that there is no triangle.
But
And
sir, if you take in the topmost figure, then if you take V2, V6 and V8, then why not it is triangle? Why are you not considering it?
no. So V2, V6 and V8 is not a triangle because there is no edge joining V6 to V8, right? To go from V6 to V8, you have to go through V7 and then to V8, but that's a square.
Okay. So
Right?
you have to directly join without
Yeah. So that's what I meant. Edge means you should be able to join from one vertex. It's like you go from one stop to another. You cannot make an intermediate stop.
Okay.
Yeah, absolutely.
So this is a 3D graph.
Yeah, it is inherently a 3D graph, obviously, yes. But a lot of the graphs, like even K5 is really a 3D graph. I mean, we are drawing K5 on the plane, but it's not a faithful representation, right? So most graphs that you will deal with, which are large enough, would typically be not representable on a piece of paper. So they are non-planar graphs, and you have to deal with them as abstract entities because you don't always want to embed things in R3 because not everything can be drawn. If you have 100 vertices, I mean, it would not be a good idea to draw them literally because you'll go crazy labeling the vertices, and if one edge goes in a wrong place, then the entire thing goes incorrect, right? So
how is K5 a 3D graph?
No, how is what?
How is K5 a 3D graph?
No, K5 is a 3D graph. See, because see what is happening. If I go back, so when I draw K5, I cannot draw K5 on the thing without intersecting, right? See, when I draw K5, what am I drawing? I'm basically saying you do this, right? I can do this, I can do that, and then I have to draw this one. You might say, okay, why don't I do this? Fine, but then you see you have to draw this one. You might say, why don't I draw this? But then I'm in trouble because how do I draw this? Right? So now I have to draw this one. I cannot draw it this way because then there's an intersection. I cannot draw it from here either because even then that will intersect. Right? I could draw it like this, but that also intersects. And I could draw it like this. Then that will intersect, and you cannot prove this, but at least by drawing. But you can convince yourself by physically drawing that there's no way to draw K5 where the edges don't intersect on the plane, right? So to actually faithfully visualize K5, you have to imagine this is like an underpass. But to make this an underpass and overpass, you literally are in R3, right? Do you get my point? Yeah. So and similarly, K6, since it contains K5, K6 is also non-planar. Yeah. Any other questions?
Sir, what do you mean by a graph planar?
Also, planar graph is basically a graph which you can sort of realize it in the plane, which means you can assign to each abstract vertex a point on the plane and assign to each abstract edge line segment joining the two corresponding points assigned to the two corresponding vertices. And the line segment should typically, you can be a curved line segment, but typically it shouldn't have self intersection, right? Meaning if I'm drawing a curve, so if I'm some sort of so if I have this and this, and the thing that I'm assigning, I can draw something like this. This is fine. Or I can draw something like this on the plane. This is fine. Okay, and I'll not draw something like this. This is just for convenience. So, but typically, if you can draw something like this, you might as well as well erase this kink and just do this, right? So the point is, for every abstract vertex, you're assigning a point. For every abstract edge, you're assigning a path, joining the corresponding points, and you do not want two edges to intersect because abstractly the edges don't intersect unless they intersect at the endpoints, right? So edges in the abstract graph don't intersect. So here you don't want two actual edges which are realized by paths to intersect. You don't want this. Right? So this is what you don't want.
Yes, sir.
Okay. So for any graph which you can draw it on the plane in this manner, you call it a planar graph. So that's a realization of the abstract graph on a piece of paper. So some graphs are planar, some graphs are not. I mean, like most abstract large graphs are not planar because they have a lot of a lot of edges, a lot of loops, and so on and so forth. So any graph that you are dealing with using in all this computer science, Facebook, and all these data, big data, most of these graphs are highly non-planar. So yeah, that's does that help?
Yes, sir.
Okay.
But can there be it in that there are forced intersections in 3D space also?
No, so the point is, see, 3D space has enough space that, see, your edges are basically one-dimensional objects, right? They're curves or lines, and so in 3D space you have enough room, right, to sort of because two lines cannot typically intersect in 3D. You can basically, if two lines intersect, you can always move one from another, right?
Yes, sir. Okay,
So
got
yeah.
it.
So shall I stop sharing now?
If there are no further questions, then it.
Okay, so yeah, I'll just wait and see if people have other questions. I can share the handout to Shanchan or one of the limit members, and if the students want, it can be forwarded
Yes.
to them.
Yes, sir. You can send me. I will.
Okay. Somebody raised a hand or something. I couldn't see. Okay. No, I cannot see anybody now. Okay, it seems there are probably no further questions.
So, Atharva Mahajan asks, what's the proof that Ramsey numbers exist?
Oh,
In the
what's
chat.
the? I see. What's the proof? Well, so I guess there are probably a lot of like modern proofs. It depends on where you want to start. I haven't looked through carefully how Ramsey originally proved it, but I would suggest you can look at a lot of these sort of modern sort of discussions on the topic where they start with Erdős's work on that, and that will probably be a good place to start reading. Because the way Erdős came upon this thing was he didn't know about Ramsey numbers at all. He was solving a different, like a happy marriage problem or something with Zekiris, and then digging through the literature, he came upon Ramsey's theorem, and then he sort of contributed in a large way, and then the field exploded. So I would suggest read a discussion or an exposition on how Erdős sort of thought about these things and how he proved some of these bounds. That would be a good place to like learn proof, rather than maybe Ramsey's original treatment, which might be slightly old, at least in language.
Okay, so if there are no further questions, maybe we can stop here.
All right. So yeah, thanks for listening.
Thank
had
you
a
very
nice-
much, sir. It was a wonderful lecture.
Thank you.
Thank you, sir.
Bye bye. Good night, everyone.
Good night, sir.